Okay, guys, welcome. It's video 3. I'm getting ready for our chapter 11 and 12 exam, and this is problem 3. So we're looking at an equations of motion example, and we're going to talk about normal and tangential frames. So given the 60 kilogram wrecking ball is attached to a 15 millimeter long cable, AB, and swings in the arc shot, right? So swinging back and forth. They want us to find the tension at point C, back here at the top of the curve. So that means it's not moving. And at B, when the velocity is 4.2 meters per second. Right, excuse me, that's not B, that's D. So at point D, so right here at the bottom. So a couple of notes about this that I just wanted to, I guess never mind, we'll see it as we go. So let's solve this. So the solution, okay, so A, we're looking for the tension, right? So as we saw in Jeff's videos, we're going to need the free body diagram and the kinetic diagram. And the way that I draw those is I draw them simultaneously. So I say, okay, here's the thing, right? So we're looking at point C. So we have a tension, right? It's going in this direction. Okay, and it's going to be equal to our kinetic diagram. And here, so this is our kinetic, this is our free body, and this really is just F equals ma, right? And this is how I keep it straight. Makes it easier for me to do the problem. So here, the ma is mass, and then this is acceleration in the normal direction. And this is mass times acceleration in the tangential direction. And the important thing to note here is that this is the coordinate axis, right? So the we're not using x and y here, we're using n and t. And the normal direction is 20 degrees from the vertical, right? So this is 20 degrees here. Here there's a weight. Right, so let's finish filling this in. There's a weight. This is our tension at C. And this is also 20 degrees. And what we're trying to find is T sub C. So if we do a sum of the forces, and let's go ahead and do this in the normal direction and see if we need to go any further. So the sum of the forces in the normal direction is equal to mass times the acceleration in the normal direction. And we can fill some of these in, right? So in the normal direction, we have T sub C minus, so this is plus, so this is minus, so minus W times the cosine of 20. And that is equal to mass times acceleration in the normal direction. We know that acceleration in the normal direction is v squared over rho. In this case, we're at the top of the curve, so v is 0, right? So we can actually just set this to 0, save ourselves some time, and T sub C then is equal to W. W is what? W is 60 kilograms times gravity, so that is 60 kg times 9.81 meters per second squared times the cosine of 20. And that is, oh, I just calculated it. I think it's 559. Double check. 553. Yeah. The calculator told me 553.1. 3, so let's just go 553, sorry, 553.1 newtons. Okay, that's simple enough. All right, and B, so B is the same thing. Again, I'm going to do this, so it just starts with this F equals MA, right? And so here, this equals this. Okay, where are we? We're at point D, right? So straight up and down. So here, this is MA in the normal direction, and this is MA in the tangential direction. What are the forces acting on this? So we have weight here. We have our tension. We'll call it T sub D, right? And this is 60 times 9.1. Okay, and so what do we do? Let's do a sum of the forces. And this time, since we do have motion, let's consider the tangential direction first, right? So sum of the forces, T equals mat. Okay, what are the forces in the tangential direction? 0, right? So that means that the acceleration in the t direction equals 0. Okay, that's good to know because that might have affected this, maybe not. I'm not sure. At any rate, now we can analyze in the normal direction. So sum of the forces in the normal direction equals mass acceleration in the normal direction, which again is this. So what we got? The positive direction is up. So this is D minus W, and actually let's just put in this. So 60 times 9.81 equals the mass times acceleration in the normal direction, which is v squared over rho. So v squared. Wait, we know that value. Actually, we know all of these. So let's, I'm tempted to just write it out. No, we already know that. So let's see, what do we got? We have 60 is the mass. And we're going to be over rho, so over 15. And v squared is 4.2 squared. And when we, okay, so if we add to this, then this is equals this plus this, and this day equals, what did I get? I got 659.16 newtons. So it's pretty straightforward stuff. The important things to remember here are that we're, first and foremost interested in determining whether it makes sense to use a normal and tangential frame, because it doesn't tell us in the problem statement which one to use. And the key with this really is that if it makes more sense to look at the moving frame, and especially if you have tension on a swinging thing, you're going to end up with the normal and tangential. And then on the exam, you will need to be doing free body diagrams and kinetic diagrams. I highly recommend just adopt this. This is so simple. Draw the thing twice, put the equal sign between it. And if you're in the normal and tangential frame, just draw that right on it. And this gives you your coordinates. Then you solve it. It's easy peasy. So I will See you in the next video.